Okay, let's solve the following second order initial value problem using the Laplace transform. So here we're given y double prime minus 3y prime plus 2y is equal to e to the minus 4t with initial conditions shown here for y and y prime. So when we take the Laplace transform of this differential equation, we'll do it term by term. So Laplace transform of y double prime minus 3 times the Laplace transform of y prime plus 2 times the Laplace transform of y is equal to the Laplace transform of e to the minus 4t. And we note that the Laplace transform of y will let it equal to y of s. So in this case, since this is a second derivative of y, this is s squared y of s minus s times the initial condition y 0 minus y prime of 0. This is minus 3, put a big bracket here, so this is sy of s minus y of 0 plus 2y of s. That completes the left side. Now the Laplace transform e to the minus 4t is simply 1 over s plus 4. Now applying the initial conditions and factoring out the y of s, so we'll factor out the y of s. So that leaves s squared minus 3s plus 2. And then we'll substitute the initial conditions. We'll put it in the other side. So that's 1 over s plus 4. The plus s is here, but that's y0 is simply 1. So there's just a 1 in front of this coefficient. I'll just put that for emphasis. And then plus y prime of 0, which is simply 5. Now here we have a minus 3 and a minus here, so that makes it a plus 3, but when we transfer it to the other side, that leaves a minus 3. Now we can simplify the right side as 1 over s plus 4, s plus 2 here. So that's how we transform this differential equation into the Laplace domain. S plus 4, s squared minus 3s plus 2, where we divide s squared minus 3s plus 2 on both sides of this equation now, plus s plus 2, the numerator, and s squared minus 3s plus 2. We can put this in a common denominator, which is s plus 4, s squared minus 3s plus 2. Well, we note here that there's a s plus 4 right here, so this would be 1 plus s plus 2 times s plus 4. Now we can simplify this. So now we can simplify this even further. S plus 4 in the denominator, s squared minus 3s plus 2. And in the numerator we have a s squared. Then we have a 2s and a 4s, which is a 6s. And then 2 times 4 is 8 plus 1 plus 9 here. Now we can use partial fraction expansion to solve this problem, and we did this earlier. Now we can factor the denominator such that this becomes s plus 4 all over s minus 2 s minus 1, s squared plus 6s plus 9. And we did this problem earlier in which we expanded this as a partial fraction expansion such that we have a over s minus 1 plus b over s minus 2 plus c over s plus 4, where we calculated earlier from a previous video that a is equal to minus 16 over 5, b is 25 over 6, and c is 1 over 30th. Now we take the inverse Laplace transform of y at s, which turns out to be y of t. So using this set of values for a, b, and c, and this partial fraction expansion shown here, we can say now that for corresponding to s minus 1, that's just e to the t with a coefficient of negative 16 over 5. Corresponding to the root 2, s minus 2, we have e to the 2t with a coefficient of 25 over 6. And then corresponding to the root of minus 4, we have s plus 4 with a coefficient of 1/30th, so we have 1 over 30th e to the 4t. So that's how you solve this differential equation using the Laplace transform technique. Note we use the inverse Laplace transform to go back from the Laplace domain to the time domain, as shown here.